Hey guys, Mr. Hartman here. Just wanted to give you an update on what we did today, Monday, November the 1st. Um, so we started with just kind of a warm up using our new heat equation. Um, and basically, what we want to make sure we understand is when we're doing this equation. So what we want to look at then is we just want to make sure that you feel good using our H or heat energy equals the mass times, oh man, this is bad, the change in temperature times the specific heat of water. And that's going to tell us how much heat was added to that water. So for example, with this question, um, our mass is 50, our change in temperature, right? We went from 20 degrees to 55, so we could say 55 minus 20 is going to give us a change in temperature. That's really the only tricky part here that we need to remember. Change in temperature of 35 degrees, okay? Then we just plug that into our equation and we remember that the specific heat of water is always 1, meaning we need 1 calorie to raise 1 gram of water by 1 degree Celsius. Okay, so if you want to practice that one, go ahead and do that one. So now, next thing we started talking about, we did a practice problem, and then we wanted to look at this idea of the second law of thermodynamics. Okay, so our second law of thermodynamics is a little bit trickier when we look at it online, because it starts talking about entropy and probability and all these different things that really are explain how it works. But what we want to know is that energy will always flow from high energy to low energy, meaning something that's hot and has a lot of energy is always going to transfer that energy to something that has lower energy. Okay. The example we use in class a lot is, whoa, coffee. Okay. So if you have hot coffee, that has high energy, right? Um, and if we leave it in a room that is cooler, like 72 degrees, we'd say that has lower energy. So as I leave my coffee in a cooler room, that coffee is then going to transfer some of that energy and lose that energy into its surroundings, right? And that coffee is going to continue to get cooler, cooler, cooler. The room temperature should go up a little bit, but it's a big room. But they're going to go until they reach equilibrium, meaning my coffee is the same temperature as the surrounding air in the room. Okay, that's this idea of equilibrium. So what we looked at is it goes from high to low. Okay, so what we did to show this was we use this model here. Okay, so this is showing kind of diffusion. So we added some particles in here. Okay, um, and what these particles represent is we're going to say that the red particles are like my cup of coffee. Okay, they're going to be higher energy. So I'm going to increase the temperature of them. You can see as I increase the temperature, they start to speed up. The blue particles are going to represent the surrounding air in the room. Okay, and you can see as I cool them down, they now have lower energy. Okay, and so what's going to happen is as I introduce my coffee here into this room temperature room, we're going to see some of the coffee particles transferring energy into the room temperature. Now, what we want to pay attention to is this number here. We can see that the average temperature in this section is much, much lower, right? And so we're going to go ahead and remove the divider. So now when we say transferring energy, each one of these little collisions that's happening, what you can see that the red particle is slamming into it, colliding with it, and transferring some of that energy. It's giving that energy to the blue particle. And that red particle then loses some energy, because we know with the first law of thermodynamics, it says energy is not created or destroyed, it's transferred. Okay, and that's what's happening here. And we always know that it's transferred from high energy to low energy. So as we watch this, then we can. Oh, I always do this. I mean to hit pause instead. But as we watch this reaction taking place, we can see these high energy particles transferring to low energy particles. We'll give it another second. But just like my coffee, right, the coffee is going to mix and start to collide with the cooler air particles in the room. But eventually we can see that this number here is starting to go down. That's like my coffee temperature, right? It was nice and hot. Now it's starting to decrease because it's transferring energy into its surroundings. The surrounding, we can see now, is starting to increase, okay? And we could see this happen until we reach equilibrium, right? That's that second part of the law, okay? So when we go ahead and pause this, we can see that they are much closer, right? We have very similar energy. That's when we talk about reaching equilibrium, okay? So that's the big thing that we talked about. Now, when we go to Google Classroom and we look at this new lab, the 2.2 lab, we are basically going to be taking a piece of metal like this, right? And we're going to heat it up. Then we're going to put it in what's called a calorimeter. And with this idea that energy is not created or destroyed, it is transferred. This hot piece of metal is going to transfer energy into the room temperature water, which is in our calorimeter. Now, we can assume then that this has high energy because it's hot. The room temperature water is low energy. So the energy that goes into the water is going to be coming from this coin. Now, if we know how much heat the water gained, we're going to be able to say that all came from our metal or our coin. And that is going to then allow us to say, hey, this is how much energy this coin lost or the metal lost. And then we can calculate its specific heat. Okay. So keep watching. I will make a video tomorrow of the lab, and you guys can just kind of follow along in your notebooks. All right. Thank you. Bye.